So for those who don't know me, I'm Enrica Soria. I'm the one in the picture on the right. And I'm very happy to present my work today on predictive drone swarms in cluttered environment. As Enrico, who presented before, I'm currently doing my PhD at the Laboratory of Intelligent Systems. And yeah, let's go to the presentation. So first, I would like to motivate my work and why we are studying drone swarms. We've been inspired by nature and in particular to an amazing swarm of starlings that can fly all together, go from one point in space to another while being cohesive, and at the same time they do not collide with each other and also with the environment. Here's a movie with more than 1 million starlings in Rome, Italian capital. And so one question is, how can these birds all together perform this collective motion so well and integrate the environment so well? And they can do it in natural spaces like forests, and they can also do it in urban spaces like cities, as we've seen in the video. And so we would like to transfer this capability to aerial robots. And here in the picture on the right, you can see one of our indoor environment for testing our swarms in the motion capture arena that we have. We have some artificial obstacles, and we want to achieve collective flight in this sort of complex environments with obstacles. And so back then in 2018, when I started my PhD, I looked at the state of the art, and I was amazed by the incredible records that Intel was hitting at that time. They had 1,000 drones flying in the sky and performing light shows. It was quite amazing. But if we look at the method that these drones use to fly together, they follow most likely pre-computed trajectories, and they fly in environments where there's no obstacles. Still, this is very amazing, but it's still a bit quite far from what birds, for instance, are capable of doing. Other examples from the research literature are this and this one. The one in the middle is one of the first robotic aerial swarms flying in real world outdoor. This is an image taken from the paper, so it's more of an animation. It's a synthetic image, but the original work was performed with 10 real aerial robots flying outdoors. They were flying though on different planes, although they could coordinate in a decentralized way. They were flying on different planes in order to avoid collisions in an artificial manner. And they were still flying without the presence of any obstacles. And as for the last example on the right, I don't know if you can see my pointer, but the one on the right.
Yes, we can see your pointer.
Oh, thank you. And so in this example, which is quite astonishing because this lab were flying 32 drones, and in research environment, we all know how hard it can be. These robots were all flying in the same plane, which means that they were able to avoid collision with each other. And at the same time, they were cohesively coordinating. And it was done all in a predefined or confined area, which means that all the robots were approaching, let's say, the edges of this flight arena, and this is why they had added a sort of an artificial rule that all the agents were following, which is the friction, in order to reduce the oscillations of the robots. But anyways, the two examples coming from the research environment, they were based on artificial potential fields. And I would like to spend a few words on this because that was at the time the predominant method that we could see being used for swarm robotics. So according to this method, the researcher defines some artificial potential field, which generates some artificial forces, and each force is associated with a certain behavior that we want to encode in the swarm. For instance, we can have cohesion to bring all the robots together. We can have repulsion to avoid inter-agent collisions. And we also have migration or alignment in order to steer all the robots towards the same point. And as I said, the last work from 2018, they also had friction to reduce oscillations around the edges of the flight arena. However, we can still see that there's a gap between this swarm that we can see here and the natural swarms. In particular, there's no obstacles, they are not flying in 3 dimensions, and they are not as reactive as birds would be. And so the question was, how do we fill this gap? And one answer that we that came to our mind and we wanted to test as an hypothesis was with prediction. And so it was nice because at that time there was a paper coming out by Jan Cousin in Trends in Cognitive Sciences saying that maybe individuals in swarms, in birds, flocks, or fish schools, maybe these individuals, they enhance synchrony between each other by interacting with the projected future state instead of only looking to the current state of the system. And so this was sort of an hypothesis to test. And at the same time, there's in the control theory, there's a nice framework, which is optimization-based control, which allows us to include constraints explicitly, and it's model predictive control. So this is why we decided to adopt this method and compare drone swarms models based on these techniques with state-of-the-art approaches based on potential field, for instance, as we've seen in the work in Science Robotics 2018. And so in the state of the art, using model predictive control, of course, is not new. And there were already some examples until this year also of multi-drone system using MPC for different kind of tasks. For instance, following pre-planned trajectories while avoiding online collisions with other robots. So in this case, the robots are assigned pre-planned trajectories, which are intersecting each other, and they can avoid real-time the collision. And we have also other examples, like the one in the middle and the last one, where each agent is not assigned predefined trajectories, but trajectories are computed online by solving an optimization problem. But all robots have different different and individual starting and end point, and while they're not in such a dense conditions, like the density of the robots is not that high, and this is what was specifically what we wanted to test. We wanted to have a sort of a large swarm of drones flying together, sharing the same environment, being cohesive and transitioning from point to point. And so this is sort of a summary of the test that we want to run. We want the swarm to start from one point in space. For instance, here, drones are initialized in this pink cube in the foreground, and they have to fly all together to the migration point, either in the forest-like environment with these artificial trees, or in the funnel-like environment by squeezing them through the tunnel. And as I said, we started by implementing a predictive model with exactly the same rule that I mentioned that the potential field-based swarm model we're using, so cohesion, separation, and migration. And we optimized the parameters of the two algorithms based on genetic algorithms on the same environment. And we tested then the two models with optimal parameters. And here on the left, you can see the the trajectories that we that resulted from this test. On top, we can see the potential field-based swarm. At the bottom, the predictive swarm. And what we can see already is that the potential field-based swarm trajectories are longer. They deflect in front of obstacles, and the synchrony is sort of reduced. And now I have to define how we can measure the synchrony. And we can do it by using a certain metrics, which is called the order, which measures the correlation of the direction of the movements of any couple of agents or individuals. And so now we can have a look at the plots. We can see that the predictive swarm could track the reference distance, which is the equilibrium distance between cohesion and separation, much better than the potential field-based swarm. It could fly much faster, as I said, without slowing all the time in front of obstacles. And the order is increased, is close to 1, correlation is close to 1. And finally, there was no collisions in both cases. So now we had a model which was centralized in the sense that even though we considered only neighboring agents for computing these rules that I mentioned, cohesion, separation, and migration, there was one single optimization problem which was solved centrally by one single computer. So there was one single problem optimizing for all trajectories in the swarm. And but with this model, we proved that we had better performance than potential field model. So prediction was actually improving our performance. This model was tested with different reference interagent distances and speeds, and it could still adapt well without generating collisions. And also it could adapt to different environments with different obstacle density. Sorry, the obstacle densities, which was what we wanted. But does this model scales with the agent number? Well, not really, because since the model is centralized, the number of variables in the problem was increasing with the number of agents, and the computational time was just exploding, so we couldn't even test it with more than 6 agents. So this is when we decided to change our strategy and use a distributed approach. As in the end birds would do, every bird solves its own problem in a sense. And so this distributed approach is made of 3 steps. The first one consists in every agent detecting a number of closest neighbors. So in the picture, the agent I is detecting the closest 3, which are highlighted in blue. Then second step, the agents are computing every agent is computing the optimal trajectory with respect to the neighbors, according to the same rule that I mentioned above. So cohesion, again, separation and migration. So they all have to get to a point which is hidden here behind the obstacle. And at the same time, they also have to avoid collisions with obstacles and with the other agents. And the third step consists in communicating the predicted trajectory, which is predicted over a given prediction horizon, to the neighbors. So each neighbors is communicating its trajectory, and local neighbors are reading the trajectory which is communicated. And so before presenting numerical results, I want to play this video to show you how this actually works in real life. We have the drones are positioned here. They are now taking off. They will go to the initial point, which is randomly distributed in the cube here. Now they're transitioning, avoiding collision, all going to the migration destination. And once they are all, or once the center of the swarm reaches the migration point, they can land.
Sorry, Enrica, there is one aspect that is unclear to me. That
Yes.
is, after they communicate their paths to their neighbors,
Mm-hmm.
everybody replans again by considering.
Exactly.
Oh, okay,
Yes.
good. I missed this little bit of information.
You're
Now
right.
it makes.
I didn't clarify that. So MPC, it's sort of a repetitive strategy in the sense that every single step they they re-optimize their trajectory of a shifting horizon. And so, yes, this new trajectory can be close to the previous one or not close. It depends on whether they are close to a sort of a stable situation or not. For instance, around obstacles, they can replan quite heavily their trajectories. Yes.
Okay, thanks.
And so here we have some experiments that we did in order to check if this approach was robust to positional noise. We have here 3 noise levels. One is 0 noise level. The second one is sort of intermediate noise level and high noise level, which is the last case on the right. And yes, we can see that there's still no collision, meaning that we have this safety distance here in gray, and we have this collision distance in red. And at no point in time, this red line is crossed. But the agents from time to time, they do go beyond the cohesion distance. And this is allowed by the relaxation of the constraints. So the constraints for cohesion and obstacle avoidance, as well as reciprocal avoidance, they are soft constraints. The agents can, from time to time, violate these constraints in order for the problem to still find a solution, but this has a cost which is taken into account into the cost function, and it's quite heavy. Reason why we don't see collisions happening up to this noise level. Noise level, which is 70% of the safety distance that we set. And so we've seen that the swarm can perform well for different noise levels, but we also tested different size for the swarm, a different size n, from 4 to 36. And overall, what we can see from all these plots, which is quite of a huge information, is that when we increase the size of the swarms, performance overall decrease, which is also what we expected. Like the problem becomes more and more complex to be solved, and so mission completion time increases. The drones take more and more time in order to get to the final destination. The order decreases, meaning that the correlation of the movements is decreasing because the agents are replanning and they are kind of going in different directions. And minimum inter-agent distance decreases as well, although it stays over the collision distance. And here the 3 different colors stands for the 3 different noise levels. I think these plots are much clearer than these heat maps. These are quite hard to be read, but I can try to interpret this for you. On this axis, we have the swarm size. So the number of agents is increasing towards the right. And here we have the noise level, which is increasing going up. And yellow colors means bad performance, in this case, mission completion time. Sorry, and it's the opposite, sorry, for the order metric and the minimum inter-agent distance, but as I said, basically the take-home message is the same. So when we increase the number of agents, mission completion time is going to be worse. Same for the order and minimum inter-agent distance. So now we have a nice framework which is distributed and allow us to scale the swarm up in terms of number of agents. The swarm is robust to positional noise, which is also nice. is rather reactive, meaning that the drones don't slow much down in front of obstacles because of this prediction and replanning strategy. But they do require communication between each other, the agents. And so this brings some fragility against outages and delays, especially if we consider dense swarms, which is what we want. And so next step is going to involve the fact of removing the communication between agents. We would like to have a communication-less predictive swarm, which can be based on other local sensing methods, such as vision, for instance, but does not use explicit communication of the predictive trajectories. And so we still have the three steps that I said before. First, the agents have to determine the closest neighbors, but this time we have to consider occlusions. We have to take occlusions into account. For instance, this agent, which is now surrounded by the red circle, won't be seen anymore by the focal agent, I here in red. And so we have to consider this in our new algorithm. Then agents are still individually solving their own optimization problem, finding the optimal trajectory. But then step 3, instead of communicating, they have to predict the neighbor's trajectory. And here there's a slight issue, because although we could say, okay, maybe they could just solve the same prediction, the same optimal problem for the neighboring drones. But the issue here is that the red neighbor, the red agent, the focal agent, does know its own neighbors. So not this one, sorry, only these two. But it doesn't know what the neighbors of the neighbors are. And so it's going to be tricky to compute the predicted trajectory of the neighbors. And so this brings me to the conclusion, because this all this chapter will be part of my next research topic. I'll analyze the safety of communication-less strategies. I'll try to analyze their robustness to noise and hopefully come up with a solution for communication-less models and compare them with the model we have. And so thanks for your attention. I'm very happy to take your question. And of course, thanks to my collaborators, colleagues, and thanks to Dario, who's the head of the lab.